And this is NASA Now, scanning space for antimatter. The crew aboard the Space Shuttle Endeavour is poised to deliver the Alpha Magnetic Spectrometer, a space-based particle physics detector. This amazing device will collect data 24/7, 365 days a year for as long as the ISS remains in orbit. That's ahead. First, here's what's happening at NASA Now. NASA says Space Shuttle Endeavour is ready to embark on its last flight. Endeavour sustained minor damage after a powerful storm in March. It will carry a highly sophisticated device called the Alpha Magnetic Spectrometer. This scientific instrument is designed to study space in search of antimatter. For decades, scientists have researched and worked to develop tests to understand dark matter and antimatter. Scientists say the only effective way to detect antimatter is in space, because in our atmosphere, the matter types collide and cancel one another out. The results from the Alpha Magnetic Spectrometer could have huge effects on our understanding of the universe. Hey, now let's take a look at the past.
July 2002, NASA researchers say a solar flare created about a half kilo or 1 pound of antimatter, enough to power the United States for 2 days. Antimatter has tremendous energy potential and could one day, in theory, power a spacecraft.
It's one of the great puzzles of particle physics, antimatter. Here to fill us in on this pioneering research into this relatively new realm of space science is NASA's Alpha Magnetic Spectrometer Project Manager, Trent Martin.
My name is Trent Martin. I'm the Alpha Magnetic Spectrometer Project Manager for NASA Johnson Space Center. The Alpha Magnetic Spectrometer, or the AMS, is a large high-energy physics experiment that will be put on the International Space Station. The experiment is designed by more than 500 physicists from 60 different institutes in 16 different countries around the world. It's designed to look for antimatter, dark matter, and to understand cosmic ray propagation from the universe. If you think of a hydrogen atom. The hydrogen atom has a proton and an electron going around the outside. The proton has a positive charge, the electron has a negative charge. Antimatter is the exact opposite. It has a proton-like thing, but it has a negative charge, and has an electron-like thing, but it has a positive charge. We have proven that antimatter exists. We've been able to create antiparticles at accelerator locations, specifically at the European Center for Nuclear Research. AMS launches on the shuttle. Once the shuttle reaches the space station, the space shuttle arm hands it off to the space station arm. The space station arm puts it onto what are called the payload attach sites outside on the truss on the space station. The space station allows us the capability to utilize the space station's power and control systems, their propulsion systems, and their communication systems to our advantage. That allows us to use most of the weight to do science. So we built a large detector, 15,300 pounds, that sits out on the truss site, utilizing those services of the space station to get the data down to the Earth so that we can analyze it on the ground. We're looking for a naturally occurring antimatter. One theory at the beginning of the universe says that at the beginning of the universe there were equal amounts of matter and antimatter. If there were, and if there are, then there should still be equal amounts of antimatter and matter in the universe, which means that literally half the universe must be made of antimatter. If it is, we will see it on AMS. The data all comes down from the International Space Station, and we send it from Houston to Geneva, Switzerland, where they will have their Payload Operation Control Center. From there, they will make sure that all the science data is in the right formats, and they'll send it out to science centers all over the world. I used to sit and think, I don't understand why we do basic research. It just seems like a waste of time. The truth is, Basic research is the foundation for what we do in applied research. So AMS is a pure basic research experiment. We're looking for foundations of modern physics. And hopefully we can find that it matches with our current belief of what physics is. But there's a possibility that we find it doesn't match with our foundations of modern physics, and we change the whole way people think.
Did you know U.S. physicist Carl Anderson confirmed the existence of antimatter way back in 1932? He discovered positrons, or anti-electrons, while studying cosmic rays. Now you know.
Now it's time to check out what's up.
2011 is a great year for sky watchers, and from now until the end of May, you can see a spectacular rendezvous of 4 planets. In the morning sky, watch for the celestial dance or movement of Venus, Jupiter, Mars, and Mercury.
Hey teachers, here's a great resource to help your students delve further into the math of antimatter.
NASA Explorer Schools features black hole math. Check out these other space math problems and have your students use simple equations to explore high-energy particle physics. Visit the NASA Explorer Schools virtual campus and look for the link spacemath.gsfc.nasa.gov/universe and look for problems 307 to 313.
Well, that's it for NASA Now. Be sure to tune in next week when we learn how scientists are developing and refining nuclear propulsion. We'll see you then on NASA Now.
NASA Now comes to you from the virtual campus at NASA Explorer Schools.